So if you all would turn to page 70, please, in your booklets, that's where we'll start. Just going to very quickly recap what we talked about yesterday. If you need more specificity on this, check out the videos I made for mass and volume. So we began this lab by recording the masses of 5 samples, 5 metal samples, A, B, C, D, and E. It's those right there. You should have ended up with 5 averages, 1 average mass for each piece of metal. Any questions about that? All right. Then we focused our attention on volume, and I reminded you guys how to use the graduated cylinders here. Let me know if you have any questions about that. We used displacement. We compared the initial volume to the final volume, and we subtracted those, and that gave us the volume of the chunk of metal, just like this picture shows up here for a chunk of gold. And then I had you, each individual, I'm Joel, so this is my table 2 here. Each individual measured the volume of all 5 pieces of metal. And then all the individuals in the group put their data together in table 3. So I put my data in this column for each piece of the 5 pieces of metal. And then the other members of my group up here did the same thing. They put their data in their column. And then for each piece of metal, I added up the 4 measurements and I calculated the average. So I added them up, divided by 4, and that gave me the average volume for each piece of metal. So at this point, I have for each piece of metal an average mass, an average volume, so I can calculate density. But we got to compile all that data first. So this is our summary of mass here. This is table 1 on page. Go ahead and turn to page 74, please. So for this table, you're not going to have to calculate anything new. You're just going to have to look at your other tables that you have, and you're going to have to pull those numbers over here. This is just your average masses for each piece of metal, which you already calculated. We just have to pull it over here for kind of summation purposes. Then you're going to do the same thing for table 2 with volume. Again, you're not going to have to do any new calculations. You're just going to pull that data that we already calculated over here. This is your average volume for your 5 pieces of metal, A, B, C, D, and E. And using table 1 and 2 here, we're going to calculate the density for each of these. So in this space, this always confuses folks what to put in this column right here for density calculations. If I said my piece of metal had a mass of 10.55 grams, I would write that. And then I would show that I'm dividing that by the volume. Let's say the volume was 30.0 milliliters, not liters. And then in this column, I'm actually going to crunch those numbers in the calculator. Take 10.55 divided by 30.0, and I would get 0.35 grams per milliliter. So that's how we're completing table 3 there, showing your calculations so that I can see what you did in case the number's a little bit off. Any questions about that? Okay. Moving on to the next page then. You are going to use this reference point. Let's back up here a second. I forgot to emphasize this. As we get our 5 experimental densities, you're going to have 1 for each piece of metal. You're then going to calculate an average experimental density for all of those. Can anybody tell me if these 5 chunks of metal, should they have similar densities? They actually should, because they're all the same type of metal. Okay? They're different sizes, but they're the same type of metal. It's the same thing that every person in this room has approximately the same density, even though we have a huge range of sizes in this room. We all have roughly a density of 0.95 kilograms per liter, because that's the average density of a human, because we're all made of the same stuff, even though we're different sizes, okay? So these densities should all be kind of similar. Now there's some error in here, so they don't have to be exact, and that's why we're calculating the average. So this is going to be our average density. I'll go ahead and write that in here. And we're going to use that to compare to a table of known densities. And let's say that my average density was 7.71 grams per milliliter. Which metal up here do you think that is most likely to be? What's the closest one?
10. What's one?
10. I think it's a little closer to steel, actually. Okay? It could be 10 because there's some experimental error here, so that's a possibility. But the closest measurement is steel, and you're probably not going to be exact because there's a lot of error in this experiment. We can talk about that later on. So at this point, what we would do is fill out this table, and would you all please turn to page 75 if you're not there already. This is table 4. So you're going to write in your box number here. You're going to write in what you calculated. That's the experimental density of the metal. So this is your calculation. Why don't you make note of that, please? Experimental is always what's actually calculated by the experimenter. And as I said down here, in this hypothetical example, that's 7.71 grams per milliliter. Based on that, I'm going to predict that this is steel, and the accepted density of the steel is 7.80 grams per milliliter. So that's how I'm going to fill out table 4 there. Any questions about how I did that? Okay, moving on to our last thing here, our last calculation. This is our percent error. And for percent error, we're going to use the formula. I'll go ahead and write that down here. Percent error equals the experimental value minus the accepted value. I'm abbreviating these. Divided by the accepted value. And that's going to give us, and that's written on page 75, by the way, that's going to give us a decimal that shows how far off we were. But we want to convert that decimal to a percentage, so the way you always convert a decimal to a percentage is multiply by 100. So we're going to put that outside of the brackets there. So let's do that for what I just calculated. I said my experimental value was 7.71. The accepted value was 7.80. And again, I'm going to put 7.80 on the bottom here. And let's crunch those numbers. Give me a moment to do that. So here is the decimal that I got. I'm really close, so I got negative 0.0115, and I'm going to go ahead and stop there. And now I'm going to multiply by 100, which means I'm just going to move the decimal 2 places to the right, but you can also multiply by 100 in your calculator. And what I get is negative 1.15% error. So don't be freaked out by the negative. All the negative means is that my measurement was a little bit under the accepted value. If I was a little bit over the accepted value, I'd have a positive percent error. Any questions about that? Okay. This video is going to be on the calendar also, so if you feel like you need to re-listen to any portion of that, please do. Headphones in the back. Otherwise, finish up the experiment from yesterday. If you think you have any bad data, go ahead and redo it. We've got time. We've got all today to work on this and finish it up. And let me know if I can help you with anything. Thank you for your attention.
You guys all, everybody got it.